So good morning everyone. Welcome to the math talk today. So today's talk is going to be taken by Sarvesh Ravichandran Iyer, SRF right? His research interests include probability, Wavy processes, and partial differential equations. Today the talk is on the Ising model. So over to you, Sarvesh.
Thank you. So let me first title my talk. My talk is going to be not the Ising model. I'm just going to call it Ising. The pronunciation is Ising model, and some sort of observations, questions, and techniques. With an eye on, with one eye or two eyes if you like, on Hugo Duminil-Copin's problem. Longest title for a talk ever. So this is the title for my talk. So first, before I start this talk, what I do is I mention the contrast. So you might know that around 5 months ago I gave a talk on this convex sets. I gave 2 talks on convex sets. Now the problem is that when I gave a talk on convex sets, it was a very easy topic, in the sense that I was able to say, this is exactly a definition, this is exactly a lemma, this is exactly a theorem. Over here, the results are way too complicated that at the level of a first year student, I can actually state a theorem with proper background. It's very difficult. So star 1. Don't expect rigor. Don't expect rigor. Expect me to give you an excellent idea of what is going on, but don't expect me to give you the complete picture, the complete mathematical picture. Star 1. Star 2 is that I am not going to talk about some things. What am I not going to talk about? I am not going to talk about specifically what Hugo Duminil-Copin's contributions were, because it turns out that the insights that Hugo Duminil-Copin had were in dimensions 3 and 4, and the techniques that I am going to show you here are going to fail in dimensions 3 and 4. So what was required to tackle them were techniques that are far more advanced than just basic ones. So I am not going to talk, not discussing. I'll tell you what he proved, but I won't tell you how he proved it or what technique he used. Not discussing Hugo Duminil-Copin's techniques. For 2 reasons. One is it's difficult, and the second is he himself is going to do it. Why should I do the work for him? Right? So there is nothing for starters. Before I start on the Ising model, let me just talk about what statistical physics is in. So, what is statistical physics in general? The idea is the following, right? You have many sort of objects, okay, and these are located in a certain pattern. So, for example, this pattern that you can see here, this is a lattice pattern. Then you can have that other kind of pattern. For example, the Pascal triangle is a pattern. So you can have many kinds of patterns like this. Each guy is to be thought of as a single unit. So I'm being vague here, but for example, a unit can be an electron, it can be an electron, or it can be a magnet, or it can be like a water droplet or something like that. So what now happens is that you have these guys scattered here, right? You have these guys scattered here, and what happens is that there are what are called as local interactions. Interactions between, so these units, right? These units, I'll be using various names. So I might call them particles, I might call them as units, I might call them as subsystems, I might call them even as atoms. But it will be extremely clear when I mention that word that I am referring precisely to one particle or one atom or something like that. So local interactions between particles. And I'm going to put a word here. So what does that mean? Well, here's an example, right? So let's say you have so this is for people who have seen the probabilistic, who attended this probabilistic method in GDRP. So let's say you have some points like this, and what you can do is you can like let's say this is a graph or something like that. Let's say this is a graph, right? This is a graph, and what you can do is you can introduce interactions across neighbors of this graph. So maybe there is something happening here, then the same thing starts happening here because this guy is connected to that. Let's say like for example there is a there's a wash basin here. So you wash your hands and the water flows from here to there, from here to there, then from there to here, and so on and so forth, right? So there is some kind of local interaction going on, and at the same time what happens is that the water that starts over here flows here, the water that is sort of here flows here, and so on, right? So what happens is that local interactions between nearby particles leads to global properties. And the idea of statistical physics is to understand what kind of global properties or study what kind of global properties can arise by creating different local interactions between nearby particles. And what is the origin typically of these local interactions? Physical phenomena. So for example, the Ising model. I shouldn't call it the Ising model, but I'll just call it the. So there is nothing called the Ising model. It's just like you have a variety of Ising models based on like what underlying setup you're working with. But so there is one underlying physical phenomena that is linked with the Ising model, and that is magnetism. So anybody knows this law called as Curies law? Can somebody state it for the convenience of the audience?
Is that the law that the magnetization increases and then increases the saturation value, something like that?
Chi equal to some constant by T minus T.
Right?
Chi equal to some constant by T minus T.
Exactly. So, okay, in my first technical term I put this, I'm using modeling. So this here, this is actually going to be a collection of terms that I think will appear in Hugo Duminil-Copin's talk as he speaks. But because he's speaking to a more mature audience, he's not going to bother defining them. So what I'm going to do is I'm going to write down those terms over here, and at the end of the talk, if anybody still hasn't got any of those terms properly, I'll re-explain them. Okay? So the first is this. So what is Curie's law? Curie's law states the following. Okay? Let's say you have an object like a bar of iron or something like that. Okay? So this is some bar of iron. Okay? Now you know that there are these states of magnetism, right? So you have, I think, ferromagnetism. You have paramagnetism. And you have another one which is called as antiferromagnetism, which is sort of out of the picture. It's there, actually speaking, in statistical physics picture, but today's talk is not going to focus on it. Okay, so there is something called anti-ferromagnetism, but we'll skip that. So what happens is that there is a critical temperature. There is a temperature critical such that when this bar is kept at a temperature which is greater than this critical temperature, the object is paramagnetic, and when this object is kept below this critical temperature, it is ferromagnetic. So what does that mean? That means that below this critical temperature, this guy exhibits magnetic properties. He exhibits a strong magnetic field. On the other hand, when T is greater than Tc, we are in a paramagnetic regime. That is to say, this guy is not magnetic anymore. So what is the sort of key feature here? The key feature is this Tc. There's just one point at which there's a sharp change in things, really sharp change in things. From like literally having no magnetism to actually having a proper magnetism. So this is the sort of key defining feature that Ising decided to try and capture with the help of his model. Or at least one of them. This isn't the only one, but this is one of them. So let me now define the one of the Ising models. This is so Hugo Duminil-Copin's work mostly took place on what is called the Ising model on the hypercube. So what I do is, instead of explaining what exactly that is, I will give you an example of what I mean. Come in. So let's say that your particles are in this form. Okay? What is the shape of this? This is what is called as a square lattice or a hypercube lattice. So when you hear the word lattice, right, when you hear the word lattice, whether square or hexagonal or hypercube or something, keep this kind of picture in mind, that you have these points which are extremely well distributed. So what does a hexagonal lattice look like? It will look like this. So you will have a hexagon, then around this point you will have a hexagon, so something like this, and so on and so forth. So that around each point you have a hexagon around, and like these guys are equally distributed. So that's called a hexagonal lattice. And I'm not going to discuss that. I'm going to discuss only square lattices for now. Now, what happens in the Ising model is that each guy is either plus or minus 1. So each guy is either a north pole or a south pole, so to speak. So either north can be plus 1 or south can be plus 1. That doesn't matter. Each guy is plus or minus 1. Okay? So this guy is plus or minus 1, this guy is plus or minus 1, this guy is plus or minus 1 with probability half. So this guy is plus or minus 1 with probability half. This guy is plus or minus 1 with probability half. So once you assign everything, then you get like a certain configuration. So for example, this guy might be plus 1, this guy might be minus 1, this guy might be minus 1, this guy might be plus 1, and so on and so forth. Now, what happens in like, so what can you say is like a stable state? A stable state is a state where negative guys have affiliation to positive guys, right? So negatives and positives like to stick together. On the other hand, if you stick in a positive and a positive together, you increase the energy of the system and therefore decrease the likelihood of that state. So the Ising model is a PMF. So I should say probability measure, but I am using the word probability mass function, which I will define on the next slide, is a PMF on some state space of plus minus 1 configurations where the probability of a configuration depends upon the number of plus 1 or minus 1 clashes. So if there are more guys that sit close to each other, then you expect that to be a bit of an unstable state. On the other hand, if there are more guys that sit sort of far away from each other, like for example, plus 1 minus 1 plus 1 minus 1 plus 1 minus 1, you expect that to be a bit of a lightning state, right? So that's the basic idea behind the Ising model. Now let me rigorously define the Ising model. For that I need to define what the PMF is. So the Ising model is a PMF on a finite set. And later on it turns out I need to put it on an infinite set, but let's not worry about that. Okay? So what we'll do is the following. We have this set, let Sn is equal to minus n plus 1 up to n minus 1 comma n to the t. Okay? So what is this? So what is this basically? Over here the lattice which I drew is like you can say it is minus 2 minus 1 0 1 2 minus 2 minus 1 0 1 2. So you can call this lattice here as minus 2 minus 1 0 1 2 square. You can think of this lattice as that. right? And what I'm doing here is I have a lattice where the size of this guy is like 2n plus 1, and the dimension, so like this is 2 dimensional, so the number of dimensions is d. Okay, now this is your state space. What is a PMF? A definition. I mean, you guys would have done this in first year, but just in case. So a PMF, so given a finite, even countable you can go for, set say capital X, a function f from x to 0 1, so it's non-negative, okay, non-negative, it's called a probability mass function, which I'll abbreviate as PMF. So Hugo Duminil-Copin will not use the word PMF, okay? What Hugo Duminil-Copin will use is, you will see the word probability measure. Okay? So I'll write this down in the technical term. So whenever he says something like there is a probability measure or something, what he technically means is there is a probability measure. So a PMF, if summation over x in x of f of capital X is equal to, okay. So what we are doing is, let me not call it f, because f is, the thing is it's a probability, so we may as well call it p, small p, and this is also I guess what Parthenon someone might have used. Right. So what we've done is, we are basically going to assign a probability configuration to each guy. So how does this probability configuration work in the Ising model? What we do is, to each configuration we assign an energy. So the energy is higher implies that the guy is more unstable. Then, because we want to study things with a certain temperature in mind, we will have an underlying temperature, a constant that is called as beta. But it turns out in statistical physics that we don't have like T for temperature, we have beta, which is T inverse. So we study T inverse instead of T. I am not sure exactly why that's the case. But having said that, temperature plus energy will give you a PMF. So now the Ising model. So what is capital X? First of all, what is capital X? Okay, you have Sn, right? So capital X is basically the set of all functions from Sn to the set minus 1, 1. So what's happening is, at each point in Sn, we are putting either plus 1 or minus 1. Okay? Now you have to ask the question, okay, so let's not call this a lemma. Let's call this a sigma, because over here it turns out that sigma is a convenient notation. Right. So now, once you have this notation, what will you do? You will have to define the PMF, right? So what is P of sigma? So before defining P of sigma, what I'll do is I'll define something called the Hamiltonian associated to sigma. What is a Hamiltonian? It's basically the energy associated to sigma. So this is called the Ising model without an external field. Okay? So in the presence of an external field, the Hamiltonian will change slightly, which I'll mention later. So what happens in an external field is slightly different. So in the absence of an external field, only these interactions count. So if you have only these interactions count, like if plus 1 and plus 1 clash, then that counts for something. If plus 1 and minus 1 clash, that counts for something. So only neighborhood clashes count. But if there's an external field, what happens is each guy will then start interacting with that external field. So that term will add up to Hamiltonian, but let's ignore that one. So without an external field, what you do is, you define the Hamiltonian of sigma as the summation. So what do? You take all pairs. You take all pairs. If they match, then you sort of reduce the energy, because that means it's more stable. So if they match, then you increase the energy, because that means it's less stable. If they don't match, that means it's more stable. So you write. So how does it work? You get to take minus sigma, where x comma y. Sorry, sigma is a function, right? So let me. Sorry, I am using sigma x and y. I change the notation and make it sigma of x. Okay. Is this clear? Is it clear where this guy comes from? Okay. Now once this guy has come, there is a parameter beta greater than 0, which is called as the inverse temperature. Okay, so given beta greater than 0, inverse temperature. Is there a beta here? There's no beta here. There's no beta here.
Sarvesh, why do we include the case? I mean, is there a reason for including the case where x equals to y in that? Like, if we just want to count the number of times.
Sorry. Why not equal to x? You're taking one place over x. And in fact, sorry, you also need y to be like adjacent to x. So you're not taking like, you're not comparing this guy and this guy. You're only comparing adjacent vertices. I'm terribly sorry about this. So you're looking at y not equal to x where y is adjacent to x. Right. Now, given this beta, you define this thing called the, so this guy is called the Hamiltonian. Okay? This guy is called the Hamiltonian. So the Hamiltonian for a system is to be thought as the energy of each guy in the system, in some sense. So where is the yellow chalk? Now, once you have the Hamiltonians, so each Hamiltonian is some number, right? So it could be potentially negative also. What we have to do is to convert it into a positive number. We will take the exponential, and in the exponential we include the beta actually. So define what is called as a partition function. So what is a partition function? The partition function, which depends upon capital N and beta, is equal to the following function. It's equal to summation over all sigma in x, equal to summation over all sigma in x, or e to the minus beta h of sigma. So let's put a subscript n here to just indicate that this n will be the guy going to infinity. So I'm just going to put a subscript n here. Okay? So Zn comma beta is basically the summation over all sigma in x of e to the minus beta hn of sigma. Okay? I'm not going to explain the origin of this because the origin of this is a bit physical and I wasn't able to grapple and get my way around it. But this guy that you see here is called as a partition function. It's called as a partition function. So again, let me write it.
One more thing, Sarvesh. What does this represent something? Because Hamiltonian says we can liken it to energy.
Yeah, it does. So the Hamiltonian represents something. I need to come up with so I have a semi-explanation which I'm not very satisfied with on why this is called a partition function. I have an explanation, but I'm not very satisfied with this, so I'm not going to mention it, sorry. Because I would much rather be safer than confuse you guys. Right. So once you have the Hamiltonian and you have the partition function, now you can define the PMF. How is the PMF defined? So PMF is just defined by, so I'm taking summation over sigma in x, right? For a particular sigma, I just take this term and then divide by the entire sigma. That will make it a PMF, right? So then P of sigma is equal to e to the minus beta h of sigma. I should put a beta in divided by the partition. Okay? This guy here, so the probability, this PMF on this set is the Ising model without an external field. So now you can ask, okay, this is a PMF. You can ask various questions, right? For example, you can ask a question such as, okay, like what's like the average magnetization? So, you know, what is the probability that this vertex is minus 1? What is the probability that it's plus 1? Or something like that. So you can ask questions like that. Those are very simple questions which I urge you to try and answer just using this definition. You can try and use this definition and answer it. But now we need to understand what are the statistical physics connotation of this, right? So one of the most important things to recognize is that when you're sliding n to infinity, this sample space x also depends upon it, right? Because xn is sigma from Sn to minus 1 comma 1. So the sample space is changing. So the first question is, if I'm letting n go to infinity and I'm studying something, I should be worried about the fact that these sample spaces are changing. Do people get that? Because the thing is, when we talk about convergence, we typically talk about convergence of random variables that are sitting on the same sample space, so that we can do something like x minus y. Because x minus y doesn't make sense if like, for example, let's say I have two random variables x and y. Okay, let's say x has sample space omega 1 and y has sample space omega 2. What does x minus y even mean? X minus y doesn't mean anything, because when we try to substitute some omega over here, if that omega comes from omega 1, then what does y of omega mean? And if that omega comes from omega 2, then what does x of omega mean? So unless we sort of find a way of putting this entire machinery within one single probability space, we will not be able to study anything about this Ising model as n goes to infinity. And the idea of what is called as a Gibbs measure is that there is a way to sort of fit everything in. So what you do is, you don't start with xn, you start with the entire lattice. So for example, this is like one particular instance, right? This is one particular instance of Sn. This is one particular instance. What I am saying is, you start with the entire lattice and put a PMF on the entire lattice in such a way that when you restrict it in some way to one of these sub-lattices, then you end up getting the Ising model. So that is what is called as a Gibbs measure, and I'm going to quickly explain what that means. Because once we have what is called as a Gibbs measure, then it will turn out that this TC, this criticality that I was talking about, is going to first manifest in the way the Gibbs measure behaves, and then it's going to manifest itself in the way that something called the spontaneous or average magnetization behaves. Okay? So this is the partition function. Calculate all basic stuff. Calculate basic statistics. So as I said, the question is, what happens as n goes to infinity? How to study n goes to infinity? And the answer is Gibbs measures. Okay, so these are called as Gibbs measures, but you can replace the word measure with PMF, because thankfully we are in a discrete setting. It helps actually that we are in a discrete setting. If we were in a continuous setting, I may have had a bit of a nosebleed. Turns out somewhere maybe 45 minutes from now we will go into the continuous setting. So then I have to check if I have a nosebleed or not. Anyway. So what is this Gibbs measure? Gibbs measure for what? Now here, I told you that the Ising model doesn't have an external field. Now what is an external field? An external field is basically, imagine you have a magnet. Okay? Now magnet Fe. Now this magnet may behave like something under some temperature. But imagine that I put another magnet next to it. Something like this, Fe or something like that. Now it's no more true that this guy will interact the same way, because this guy will start affecting this guy. So what will happen is that in the Ising model, you cannot unfortunately only consider the Ising model without an external field. You also need to go for the situation when there can be an external field, because it turns out for Gibbs measures that, so here's the question, right? So the point is, like, let's say you know, I draw that same lattice. Okay, so this is what, -101 square. Okay, now the basic problem is that if I'm putting a PMF on ZD and I want to make sure that the Ising model is sort of the case here, then what do I define as outside, right? So there are many points over here. What do I make? How do I sort of design the PMF so that these, I mean, what should be the behavior of these points so that the Ising model is what happens within just this boundary? So, because see, the problem is this guy is going to interact with this guy. This guy is going to interact with him. So there's going to be some outside to inside interaction. And because of that, we need to understand how to model that using this idea of Hamiltonians before we go to Gibbs measure. So let me explain that. So we're on a hypercube. So what is everybody knows what ZD is, right? Everybody knows what ZD is, right? D-dimensional integer vectors. Okay. So suppose we take V subset of ZD. Okay. We take a V subset of ZD, and what we will do is we will define the Ising model on V. So let's say, for example, this is the lattice. I'm not saying that V needs to be shaped like a lattice. Like V could have some weird shape also. That's also fine. Like for example, V could be this set. Something like this, which is not a lattice shape, but it's something. Could be anything. Okay. What we'll do is we'll make sure that we can somehow define an Ising model here while preserving like these external interactions. So how do we do that? Given V in ZD, you will have a Hamiltonian for all configurations. So now let's define this big omega. Okay? Big omega is all sigma from ZD to plus 1. So this is like the ultimate sample space. If all the xn's had this sample space, then we can talk about xn converging. Or then we can say that okay, xn are on the same sample space and we can do something as n goes to infinity. Otherwise, there are different sample spaces, so you cannot do anything. So this hopefully is like your target sample space. And the good news is, if I'm not wrong, this is countable. Not sure whatever. I think it's not countable, huh? Not countable, right? Okay, let's not worry about that. Let's not worry about that. Okay? Because it turns out I think you can anyway do things without worrying. So then you won't get a PMF, then I have to mention a problem in here. But I'll gloss over that. Okay, so suppose you have a finite set V in ZD. A finite set V in ZD. What you will do is you will define the Hamiltonian for H V of sigma. Okay. Now, what is H V of sigma? It is basically the following. Okay? What you do is, of course, you will take first x not equal to y in V such that x and y are neighbors, and you will take the usual interaction minus sigma x, sigma y. Okay. Now remember, I do that lattice. This term is for all guys that are both inside V and which are interacting with each other. Now what happens if one guy is outside V and one guy is inside V? That term also needs to come in, right? So x in V, y not in V, or sigma x. So this kind of Hamiltonian is formed, and what you do is once you form this Hamiltonian, this will then give you.
Is there a negative sign in the first summation?
I put it.
Okay.
So this will then give you a PMF on configurations sigma which conditioned on sigma being fixed outside. Fixed outside.
Sarvesh, wouldn't this be temperature dependent, so we should get HV?
No, Hamiltonian is quite temperature. There is no temperature in the Hamiltonian. The temperature only appears in the partition function. Okay, there is no temperature in the Hamiltonian. Okay. So what we'll do is the following: to define sort of this, to define the Ising model on an external field, we'll first fix the external field. So what does it mean to fix the external field? Sigma will be fixed outside this finite set. We'll assume V in ZD is finite for the convenience of making sure that this is a PMF. So fixed sigma outside V, and then we are looking at this Hamiltonian conditioned on those boundary values being what they are. This is a new Hamiltonian. Based on this Hamiltonian, you will get a partition function in the exact same way. So z of n comma beta is summation over all sigma from V to plus minus 1 of e to the minus beta hn of sigma, where hv of sigma, where hv is given like this. So this PMF is what you want at each V, right? Now a Gibbs measure is basically a measure that is actually, it's a measure here, but the way it behaves is that when restricted to each V in ZD finite, in the sense that when you condition on for each finite set B being fixed outside that set B, inside it behaves exactly like the Ising model. So I write that in words because it's not extremely clear, but it's not extremely clear. And the problem is that set became uncountable. For some reason my sleep yesterday I thought it was countable. That's okay. Fine, actually at this point I'll choose to be unclear, I don't mind. So let's say I'm not going to be clear.
Why do you care about its countability or uncountability?
No, because I defined a PMF and I said the PMF is only for countability. That's the problem. Otherwise I can just call it a probability measure and escape. Arey, if I need to escape, I have thousands of ways. So, definition of probability measure. Okay, this is not a PMF anymore. This is not a PMF anymore. I'm extremely sorry because this is an uncountable set. But for those who really want to know what a probability measure is, let me know outside of it, and I'll explain it properly. So, a probability measure on omega. So that is to say, with sample space omega, is called a Gibbs measure if for all B finite subset of ZD is called a Gibbs measure for the Ising model of ZD. For the Ising model on ZD. If for all V finite in ZD, the PMF of sigma from V to plus minus 1 conditioned on sigma fixed outside V is the Ising model with Hamiltonian HE. So what I am saying is that I cannot to put all these pictures together, to put all those SNs together for different values of n. What I'll do is I'll define a single probability measure here such that on each finite set it does what I want. On each finite set, I can get the Ising model. So this idea of Gibbs measure, and of course I'm being very specific here. So this is the Gibbs measure for the Ising model. Is that it's a probability measure which somehow ends up capturing what you need at every finite scale while actually being an object at an infinite scale. So unfortunately I've been a bit not very rigorous here, but that's okay. This explanation is kind of good enough. Now, of course, you might want to ask this question. Okay, like does a Gibbs measure even exist? So, does Gibbs measure exist? 1. 2. Is it unique? Obviously. Okay, is it unique? Now, it turns out that for this question, this critical temperature comes. So, here is a theorem. This theorem is due to Ising, and it's due to Eisenman, is it? I don't recall. Sorry. So, the D equal to 1 is due to Ising. Et al. Okay. So, in dimension equal to 1, for all beta greater than 0, there is a unique Gibbs measure. Okay. By the way, this so it might not be clear how like the Gibbs measure is like coming back to that magnetization problem that I said, but don't worry about that right now. That I'll come to in 5 minutes. What time is it?
I have one question. What exactly does condition on sigma fixed outside V mean?
I'll explain. So, what you're doing is sigma is set of all functions from ZT to plus minus 1, right? So when you are when you are talking about this Hamiltonian is defined only for functions from b to plus minus 1. So if I need to define it from b to plus minus 1, I need to fix everything outside. That's what I mean. So it could be fixed to anything. It could be fixed to minus 1, all minus 1s outside. It could be fixed to all plus 1s outside. It could even be fixed to something random outside. But whatever it is fixed to, whatever happens inside is the Ising model of this Hamiltonian. Okay? That's fine. I knew this topic would be a bit difficult to explain. Okay. So what happens when d greater than equal to 2 is that there exists a critical temperature beta c that's greater than 0 such that when beta is less than beta c, then you have a unique Gibbs measure. But when beta is greater than beta c, I'm not going to talk about what happens when beta is equal to beta c. I believe when beta is equal to beta c, you still have unique Gibbs measure. But so when beta is greater than beta c, you have non-unique Gibbs measure. So suddenly things break. There is more than one way of defining this Ising model. It feels like now there's more than one way for things to go to, for n to go to infinity. There can be two different behaviors that you can observe, 2 or 3 different behaviors that you can observe. So this beta c is greater than 0, and this phenomena that you see over here in general has a name. So this phenomena, the fact that there is a temperature before which things are different and after which things are different with respect to some property is called as criticality. So it's called as criticality, it's also called as phase transition. Right? So these two guys are there. Okay. So now what does so this is one thing that I mentioned. Now let me come to the actual magnetization part. So under this Gibbs measure, you can study some quantities. And the thing is, what do we want to study? Well, I told you, right, that at low temperature there is magnetization, whatever that means, and at high temperature there is no magnetization. So we need a measure of magnetization. That's what we need. And I'll define that. So I am using the yellow chart. So this is also called as spontaneous magnetization. Okay. Now you have this Ising model, right? You have the Ising model, and you have the Ising model now under this external configuration and whatnot. So once you have the Ising model, you can now look at the average spin at each point. The average spin will tell you how likely a guy is plus 1 and how likely a guy is minus 1. Now if it happens that a lot of guys are plus 1, then it's magnetized. If it happens that a lot of guys are minus 1, then it's magnetized. But if the plus and minus 1s are cancelling each other out, then there is a lack of magnetization. That is going to be the effect. So define. So we are now in the Gibbs measure setting, in the sense that we have omega is sigma from zd to plus minus 1, and there is some Gibbs measure setting on it, some Gibbs measure on it. So if you notice the theorem, there is always a Gibbs measure. It may not be unique, but there is definitely a Gibbs measure. Okay? So you define what is it? Correct. So you define the average magnetization as follows. So M is equal to 1 by. So you take those lattices again. Okay, you take those lattices that I defined. So you have those Sn, which is basically minus n comma minus n plus 1 to n whole to the d. So that's what it means to be the hypercube lattice. And then you define. So you take now b is equal to Sn. So it's a finite set, right? So you take b is equal to Sn with some kind of external field outside, anything, and you will get the corresponding Ising model inside. For that Ising model, you will have the Hamiltonian, you have the partition function, and so on, and you define this quantity m n comma beta is equal to summation over sigma from Sn to plus minus 1 of sigma I. Sigma I is the spin at that point times the probability that this configuration is attained. What is that? That's just e to the minus beta hn of sigma upon this partition. So this quantity is called as a spontaneous magnetization. Does anybody want a better explanation of this expression? So what am I doing? This is the probability that the configuration omega is what happens, and under omega happening, this is the spin at, sorry, what am I doing? Oh, sorry. Yeah, perfect. This is correct. So what am I doing here? I am taking a side. Okay? So there is a side. Where is that chalk on? So there is a side here. Okay? Now the Ising model is taking place. According to the Ising model, the probability of a particular configuration sigma is this guy. Under that configuration sigma, the spin at the point I is sigma I. And I take the average over all I because I am looking at the average magnetization. Now where is Mn? Mn is thankfully for us, because we are in this Gibbs measure setting, a random variable on omega. It is not a random variable on just sigma Sn to plus minus 1. Otherwise we have the same problem of different sample spaces, right? So thankfully Mn's for each value of n are actually on the same sample space omega. And Mn is the spontaneous magnetization. Now you can ask the question, as n goes to infinity, what happens to n? As n goes to infinity, what happens to n? So the question is, as n goes to infinity, what happens to n? And the answer is that, just as you would expect, this Curie kind of thing is observed. So for the same value of beta c, so this theorem, there is a beta c which comes as a result of this kind of splitting of non-uniqueness of Gibbs measure, right? The exact same beta c comes in this theorem. So theorem, first of all, in d equal to 1, for all beta greater than 0, this random variable Mn, it converges to 0 in probability. So what does that mean? Regardless of the temperature of beta, I push n to infinity, I will not get any average magnetization. If d is greater than equal to 2, the same beta c here, so beta c as in Gibbs theorem, beta c as in Ising et al. Beta greater than beta c, sorry, beta less than beta c implies that Mn goes to 0 in probability, and beta greater than beta c implies that Mn doesn't go to 0 in probability. So there's actually a characterization of where it goes, but for now it's sufficient to say that it doesn't go to 0 in probability. It turns out it actually goes to a Bernoulli random variable. So okay, fine, I'll make that more clear. It goes to a random variable, call it say y, where y depends on beta, where y beta is equal to some m beta with probability half and minus m beta with probability half, where m beta is not equal to 0. So roughly speaking, what this is saying is that either it goes to some positive magnetization or it goes to exactly the opposite of that with probability half each, where that amount of magnetization is definitely a non-zero quantity. So this guy here, this theorem, is the proper explanation of Curie's law. So if you want to say how does Ising model explain Curie's law, this theorem is a secret in some sense. Right? Okay. So now I need to come to the question of, dimensions d equal to 1, 2 and 5 and 8.
If I want to
Say a few words what convergence in probability is.
Sure. Not many people know that, right? I'm sorry. Yeah, right. Okay, I'll explain that. So what does convergence in probability mean? It means the following, okay? So given convergence in probability. So for convergence in probability, it's very important that all the random variables are on the same sample space, okay? Given x1, x2, x3, which are random variables from omega to r, let's say, the same omega, which doesn't depend on the index set. Xn is said to converge to a random variable x, which is also from omega to r, in probability if for all epsilon greater than 0, limit n tends to infinity of the probability that mod xn minus x is greater than epsilon is equal to 0. So in some sense, in probability, xn and x are getting closer to each other. So what's happening here is that in probability, where the probability is decided by the Ising model conditioned on the values outside, mn is going to y beta in probability, or mn is going to 0 in probability. That's basically the point. Okay, right. Now I need to explain, wait just a second, sometime spontaneous magnetization. Yeah, okay, I need to explain the following, right? So what happened was that Ising discovered this theorem for d equal to 1 in his first paper. He introduced the model and then he said in d equal to 1 there is no phase transition. And then he said, okay, based on this I'm going to make the very loose and stupid prediction that there's actually no phase transition in higher dimensions also. So Ising's prediction was that this kind of theorem actually held in one dimension, and he was horribly wrong. He was horribly wrong because you can literally see it holds in literally no other dimension. So the first person to doubt that was a person called Peirce, another physicist called Peirce. And Peirce introduced an argument called the Peirce argument that basically shows how you can produce magnetization. Okay? And what he does is he connects the Ising model to another model called as a percolation model, which I'm going to put up here. I'm not going to define the percolation model very formally, but you can easily understand how it can be done. Let's try to just show you how this works visually, right? So let's draw the lattice. Okay, let's put some spins here and there. Let's say this is plus 1, this is minus 1, this is minus 1, this is plus 1, this is minus 1, plus 1, minus 1, plus 1, minus 1, minus 1. Okay, what you do is you join adjacent points that have differing spin. Okay, so for example, you join this there, you join this there, you don't join these two, you don't join these two, you join these two, you join these two. You join these two, you join these two, and you join these two. You join these two. This. So every pair of adjacent points is joined. Okay, in this lattice. What do you think you get out of it? What happens when you join all the points? What do you think?
The number of opposite pairs essentially.
Yeah, of course. But what kind of object does it look like?
The graph.
Exactly. So what we have done is, from a model that involves spins, we have gone to a random graph model. And this random graph model, it turns out that the probability measure for the random graph, because of this kind of correspondence, is related to this entire Ising model PMF. Okay, so this model that you see over here is called as the percolation model. So the percolation model is the model where you start with the Ising model and then connect pairs of points which are adjacent to each other and whose have the opposite spin. Now, watch this. This is beautiful. What does it mean for an object to be magnetized? For an object to be magnetized, it means that there must be sufficiently minus ones or sufficiently many plus ones. Okay, in some sense, right? So what Pearl's argument does is the following. So what he does is, let's say this is a lattice. Okay, imagine that you have a path like this, like a loop or something like this, like a large loop of some sort. And in this large loop, what will happen is that because of the way this large loop is, over here there is no edge from here to here. Let's imagine that there is no edge from here to here. No such edges exist. What will happen is that here the charge will be very likely something. So it will be something like a -1 or something like that. And outside it there will be a very large charge, like a +1 or something like that. So Pearl's argument is the idea that you can create these boundary walls, or with high probability you can create these. Pearl's argument. Use population model and separate regions involving into ±1 regions using boundary walls. So what Pearls does is, in dimension d equal to 2 and in dimension d equal to 3, he was not able to go beyond that unfortunately, he shows that with high probability these kind of boundary walls exist. So what happens when you have a boundary wall? It turns out that when you have a boundary wall, you will have like a very small amount of charge here, and on the outside you have a large amount of like charge of one type, either a plus or a minus. So either the plus will dominate the minus or the minus will dominate the plus. And the same thing will happen for large n, and it turns out that this will manifest in this limit not being equal to 0. So I'm not going to go too much into the details of this argument. The details of this argument can be found, for example, in a book by John Bobbier. Forgot the name of the book. Sorry, I'm extremely sorry. I think it's called Statistical Models in Physics. This is a book by John Bobbier. He covers this Pearl's argument in a lot of detail, and he covers Gibbs measures and everything.
Sorry, what do you mean by charge inside that boundary wall? Just the sum of plus minus 1?
Yeah, exactly. So in some sense, like, what we're doing is we're sort of separating the -1s from the +1s using a boundary. And Pearl's argument is that with large probability you can kind of separate them. And what happens when you separate them? When you separate them, you end up getting a magnified object in some sense, because you have like a defined north area and a defined south area. So Pearl's argument is something that our Mr. HDC will mention. Okay, so this is Pearl's argument. Now let me quickly mention to you why dimensions 1, 2 and 5 or greater are actually what are called as trivial. Okay, so physicists refer to them as trivial, mathematicians refer to them as sort of computed, or like everything is known. So it turns out that, so dimension 1, as I told you, there's nothing critical, there's absolutely nothing critical going on. Ising did everything. In dimension 2, Pearls, using this Pearl's argument, showed that there is some critical phenomena going on. But it was a contribution of a physicist by the name of Lars Sager, who I think in 1942 showed that, he roughly speaking showed this, everything in dimension 2 is what is called as exactly computable. So the point is, you have exact formulas for a lot of things in dimension 2. And in dimension 1 also you have it. So in dimension 1 it's done in Ising's paper, but that was much easier to observe. That is so easy to observe that I have it written down, but I don't have enough time to discuss it. So everything in dimension 2 is actually exactly computable. In particular, there is this quantity called the free energy. That's actually exactly computable. So because of this exact computability, It's like, I mean, if you know things explicitly, it's easy to analyze them, right? It's only when you don't know things that it's difficult to analyze them. So dimension d equal to 2 was solved entirely by the formula that this guy gave for the free energy. Because he gave a formula for the free energy, and it turns out that formula ended up giving the asymptotics of the Hamiltonian. It ended up giving the asymptotics of the Hamiltonian, so then it ended up giving the asymptotics for the partition function. And once you have the partition function, then you're easily able to analyze the measure. Because you have the Hamiltonian, you have the partition function, which means you have the measure, you have the PMF, and then it's easy to analyze a question like either the magnetization question or the this one. In fact, Lars Onsager's calculations were so amazing that in 1953 or something, they showed that beta critical in dimension 2. So beta critical is this Gibbs measure beta criticality, actually has an exact value. So let's not debate why it is this value. That is a bit difficult. But they showed that beta critical in dimension 2 is actually equal to half log of 1 plus 2. So if you ever see this in HDC slides, you might want to wonder if some dimension 2 phenomenon is going on. In any other dimension, beta critical's value is not known. It's not known, neither is asymptotics known. Like, okay, I should not say that. In like dimensions 5 and above, you have some asymptotics for DC, if I'm not wrong. But I'll explain why now dimensions 5 and above are better. I'll explain. And that I think will be the last thing I do. After that, whatever I do will be inaccessible to undergraduates, I guess. So, because I plan to talk about something called renormalization and Gaussian free field. So that is only for a little bit more of an advanced audience. But anyway, this will be the last thing I'll talk about. So dimensions 1 and 2, everything is computable. Okay. So this is the sort of key thing that you should take away. So everything is computable in the sense that everything is explicit. It's easy to calculate it. It wasn't easy to come up with it, but once you know things, it's easy to calculate. So this is the reason why Hugo Duminil-Copin will say that dimensions 1 and 2 are easy. Now, why is dimensions 5 and above easy? 5, 6, and so on. This is also described as what is called as trivial. Okay, and the reason why is because the Ising model is a very complicated model. If there was some way to simplify it or make an easier model out of it and analyze that model and then show that the Ising model is close to that model, then life would be great. And what happens is that there is such a model, and that model is called as the mean field interaction. So the mean field interaction is it will have a slightly different sample space. It will have its own Hamiltonian, its own partition function, which will be extremely easy to write down. So easy to write down that you get back to this everything is computable, explicit kind of situation. And it turns out that the mean field interaction excellently approximates the Ising model in dimensions 5 and 6. To the extent that what can you get under mean field interaction? You can get results such as, for example, you can get what beta c might look like. That is one I believe you can get what beta c might look like. The second is you can get what behavior is near beta c. So remember that constant m beta that I talked about. That constant m beta is the amount of magnetization in the limit. What is, like, as beta goes to beta c, is it even true that m beta goes to 0? So let's say this is the graph, okay? This is a graph where on this side you have beta and on this side you have m beta, okay? Wait, I'll make sure this is visible right away. So in this graph, we know that at the point beta c, where beta is less than beta c, we know it's 0. But after this, we only know that it's greater than 0. We don't know that it's something like this. It could be something like this. It could be something like this. It could even be something like this. So we are not sure about the behavior. What the mean field interaction does is it accurately provides a description for this behavior. At least near beta c, we know kind of what happens, like at what rate it rises. We know it's continuous. So according to mean field interaction, we know that the limit from this side is 0. We also, I believe, know that the decay, like how quickly it comes, what function, what rate it comes to 0. So that is also predicted by mean field interaction. What I'll do is I have like, I think like close to 10 minutes left. In that 10 minutes, what I'll do is I'll talk about what mean field interaction is. After that, I'll ask only interested audience to stay. Because at that point, I'm going to go into some technicalities. And at that point, I really had to read like some hardcore physics papers to clarify things. Right. So, what is the mean field interaction? So what I'll do is, because my talk is ending in 10 minutes, anybody who wants to know about what I talk after that will have to meet me during lunch or something. Or meet me when I'm like collecting coupon money or something. Okay. Mean field. So, all of you have seen like concentration inequalities, right? Like Markov's inequality, Chebyshev's inequality, is that right? All of you have seen Markov and Chebyshev's inequality, or should I recall? Have you seen? You seem to say no. Disha? Yeah. You've seen, right? No. Okay, I'll say. Just for convenience. So, what is a concentration inequality? A concentration inequality is a statement that a random variable stays close to its mean. For example, what is Markov's inequality? Markov's inequality states that if you have a random variable x, which is, and if the expectation of x is finite, then the probability that x is greater than t. Okay, sorry, not Markov, but Chebyshev. Not Markov. Chebyshev is the concentration, Markov is this guy. So x is no need to be greater than equal to 0. You just need expectation of x and expectation of x square being less than. Okay, the probability of x minus expectation x greater than t is less than equal to the variance of x upon t, right? Right. So what does this tell you? This tells you that, okay, sorry. So with high probability, if the variance is small, x is close to its mean. X is close to its mean. Now what we are going to do is, we are going to say that the entire Ising model is going to be close to its mean. So this is one random variable. What does it mean for an entire model to be close to its mean? I am going to explain now. And the thing is, in dimensions 5 or greater, it is reasonable to expect that model to be close to its mean. Whereas in dimensions 3 and 4, that is not true. So in dimensions 3 and 4, the basic difficulty is that neither of these techniques work. Neither does a mean field interaction work, nor does a integrability or an exact computation argument work. So what happens is the following, okay? So let's say again this is your lattice. Okay? Now in this lattice, how many interactions are there? How many possible edges are there? So So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 12 this side, right? So there are 24 edges in total, right? Whereas if I just look at the vertices, number of vertices, that will be what, some 16 or something like that, right? So what you get is that what we will do is, instead of looking at point-to-point interactions, we will fix a point, okay? So the idea of mean field interaction is the fix a point, particle, whatever, etc. Particle, etc. Average the environment around it. Then look at its interaction with the average environment. So if this is a bit complicated, I'm sorry, I'll clean it. Okay? Look at its interaction with the average environment. And the fourth is treat different points independently. Treat different points independent. So the idea of mean field interaction I'll explain now using this diagram. Okay. So say suppose you're looking at this point. If you're looking at this point, instead of thinking about what this and this interaction are, just take the rest of the lattice, find some mean of it, and treat that as one point, and then look at the interaction between these two guys. Now do the same for this point. For this point, let's say you have the lattice, average out the rest of the lattice except for this guy. That will be one point. Find this interaction. Then do that for, let's say, this lattice point. So avoid this lattice point, take the average of the rest, take that interaction. How many such interactions are there? There are 16 such interactions, all of which are independent. These interactions will have a different Hamiltonian, and thankfully that Hamiltonian, as it turns out, is much simpler. So what I'll do right now is, I actually had a derivation, but instead I'm going to skip that derivation, and I'm just going to give you like the direct Hamiltonian. The reason why I want to show you the Hamiltonian is because I want to tell you that actually the mean field interaction, the Hamiltonian is much easier to understand. So what is the Hamiltonian here? So I'll just write it as a theorem. So this is mean field Hamiltonian. Okay. So the mean field Hamiltonian HMF of sigma is, I should not put is, put approximately, because it turns out that I'm making an approximation, right? I'm averaging over the environment and I'm equating the average to the interaction. Actually speaking, there might be some fluctuation. It's not necessarily that x is equal to expectation of x, right? So I'm averaging out the interaction, but what happens is that HMF of sigma is approximately the following. So what to do? So let's say the lattice was Sn, right? So let's say its lattice size is what? Let's call that as Sn. So this is the lattice size of Sn.
Sarvesh, to change the chalk, it's not visible.
Not visible. This is,
Somewhat.
is this visible to everybody? At the back, again? Okay. H mean field of sigma is approximately something, some constant here. This constant depends upon Sn, so it depends upon the size of Sn, it depends upon some kind of average charge and so on. Let's forget about that. C minus M, this is some kind of average charge, beta summation, it is there beta. Oh no, Hamiltonians don't remember beta, I just said that right now. So minus M.
Sarvesh, there are some chalks there.
Oh. Okay, I'll just put it as C1 minus C2 summation over sigma I equal to 1. That's all. So now what we've done is, if you note, what is the difference between the two Hamiltonians? The earlier Hamiltonian, I was considering like ij, I adjacent to j. Over here, there is no such ij, I adjacent to j. For each point I have done that Hamiltonian separately and I have just summed it. So these constants here, C1 and C2, they depend upon the size of the lattice and some kind of average magnetization. Let's not worry about that. But the thing is, this Hamiltonian is much simpler. Now using this Hamiltonian, what will you get? You will get Z mean field of sigma is just summation over sigma from Sn plus minus 1 of e to the minus beta HMF of sigma, and then you will get the associated probability measure. This probability measure is much easier to analyze than the Ising one. Okay? So the key takeaway, so let me write that down in a box, and that will be the last thing I say for today, for the basic audience. So last takeaway. In dimensions n d greater than 4, so that is to say d equal to 5, 6, 7, and so on, the Ising model is accurately represented by the mean field. So this is the reason why. So hence questions about the Ising model in dimensions greater than 4 are quote unquote known, easy or doable, whatever. So take the basic technique in dimensions greater than 4 for the Ising model is to go to the mean field. Whereas in dimensions 1 and 2, it is to use the exact formulation, the exact formula for the partition function, the exact formula for the Hamiltonian, and so on. So now, because dimensions 3 and dimensions 4 are neither covered by this nor covered by the exact computation, Hugo Duminil-Copin, in his Fields Medal winning works, devised techniques to analyze the Ising model in those settings.
Sarvesh, why this technique does not work for 3 and 4? Is it
Because I told you that the model needs to be approximated by the average.
Yeah.
That approximation absolutely fails. That fails in dimension 3 and 4. If you want me to give a more accurate picture, okay, so there are like 2 minutes to 12. I'll stop at exactly 12. So there are 2 minutes to 12. The point is that, essentially speaking, there is a principle, okay, this is just a principle. If you think about it, if you think about a random walk in high dimensions, it's very unlikely that it comes back onto itself. It has this tendency to spread out. So because of that, phenomena in high dimensions also spread out and average a lot. So in high dimensions, there is concentration inequalities can hold better in high dimensions simply because things spread out better and then tend to average out better. So that's just like a high dimensional thing. In high enough dimension, concentration inequalities occasionally or quite often, I should not say occasionally, I should say quite often improve. So improve meaning what? Improve means that you will actually get, like, if you are taking x minus expectation of x, that probability, let's say probability of x minus expectation is greater than p or something like that, that might be better and better with increasing dimension if x satisfies some condition. So for example, if there is a condition called sub-Gaussianity or something, sub-Gaussianity implies dimension independent concentration. So you can actually get something like a right hand side which is completely independent of the dimension, which is quite a surprising thing. And for example, if you change x to some kind of random walk on rollers or something like that, and you consider like distance to stationarity, things like that, there it turns out that with dimension things actually improve. So that something like that happens here also. Concentration equalities quite often improve with increasing dimension. Basically because more averaging occurs. More averaging occurs. Okay, so this is where my talk ends for like a basic audience. 1.5 I planned. I have another 1 hour worth of material, but let's just say that it's a bit difficult. So there is something called renormalization that I will talk about. Then I plan to talk about something called Gaussian free fields. And to talk about Gaussian free fields, I'm extremely sorry. Like, to understand, for example, why a Gaussian free field limit is trivial, to understand why people don't like such limits, it will take a bit of hard work.
Sarvesh, like when we are fixing the point and averaging out, so what exactly we are averaging out? The magnetization of
You're averaging out the magnetization of the rest. Like the interaction of the rest of the guys, you will kind of average them out. So that will be treated as one single point. So it's like, for example, in physics, when you do like rigid body studies, you kind of approximate everything by the center of mass, right? So you kind of create like a set that you kind of treat that entire sub-Ising model as like a center of mass at one point, and then you take that.
So that wouldn't be like independent of any fixed point also, because then you are just taking the point, but the remaining number of lattice points are the same.
Huh.
That's why that constant will appear, I guess.
Yeah, that's where the constant. Actually, the constants appear as approximation. So what you do is you assume that the average magnetization of each side is the same, and so on and so forth. So under some basic assumptions, and those basic assumptions work out in high dimensions because there's a lot of averaging in high dimensions. So this is what you need to do. Tomorrow when you go to Hugo Duminil-Copin stuff, let me go through this one last time. Okay? So Ising model definition is done. You guys know what a lattice is, basically speaking square, epsilon, whatever. You know that a PMF and a probability measure are roughly speaking the same. I've shown you what the Hamiltonian is for the Ising model and for a couple of related models. I've shown you what the partition function is. I define what a Gibbs measure is, which is to make sure that the sample space is the same. I define what is a critical or a phase transition using the Gibbs measure idea, the existence of beta C. Then I define what is Peirce argument, which is the idea that you have a definite boundary wall in order that to create a north and a south pole, it is saying north and a south pole, and create magnetization. And I define what is called as a mean field interaction, which is this kind of resolution of the Hamiltonian into a simpler form, which turns out to be an excellent approximation of the Ising models in dimensions 5 or 10. That's all. Now I need some water. So what can the mean field predict? The mean field can predict beta C. So it can predict beta C, which is the critical temperature. It can predict, as I told you, what is like the behavior near beta C. And it can also predict, so what the behavior near beta C. So typically speaking, there are like some terminologies that they use. It's called as first order and second order interaction. So first order interaction is basically, so first order is supposed to be like a law of large numbers, and second order is supposed to be like a C and D. So understanding m beta at the first order and at the second order level, I am not going to be precise at this point, can both be done using the mean field interaction, and the mean field interaction is so damn powerful that it will give you both these interactions, both these first order and second order interactions correctly for dimensions 5 and 5. Whereas for dimensions 3 and 4, so what is known in dimension 4 is that Hugo Duminil-Copin showed that continuity. So I told you, right, that at beta equal to beta C it is 0, and then like I didn't tell you know that it's positive beyond that, but like I told you, it could be anything beyond that, right? Hugo Duminil-Copin at least showed that it is continuous at beta C. So he at least showed that the limit from beta tends to beta C from above is 0. He showed that much, but he did not show, for example, at what rate it is coming and so on. He didn't show at what rate it is coming. So that is a different topic for a different day. Dimension 4 is slightly easier than dimension 3. In dimension 3, there is literally only one technique, which is an extremely difficult technique, which we will discuss in his 4th or 5th lecture, called as the conformal bootstrap. This technique is extremely difficult to understand, because this is, I don't even know how to explain this. I don't even know how to explain it to like an advanced audience. Yeah, so that is the state of affairs in dimension 3 and 4.
So since you're talking about high dimensions, give the reference of when I was book.
I'll give like a list of 5-6 references at the end. Where is the person who usually asks for references?
Yeah, okay, you can send the references below.
Yeah.
You can send the references on the board of this.
Oh, you mean I write it down now?
Yeah.
Okay.
Yeah, that will be.
So first we'll start with the note of Hugo Duminil-Copin himself. Hugo Duminil-Copin has written an excellent note which contains literally all these techniques. Not to the highest amount of detail. Okay, so not to the highest amount of detail, but nevertheless it does contain them. So Hugo Duminil-Copin RF. Hugo Duminil-Copin, 100 years of the 100 years of the Ising model on the hypercube. Okay, 100 there is a note by Martin Herer. Martin Herer is a field medalist from 2014, but he discusses the contributions of Hugo Duminil-Copin. So this is nice to read. Like Hugo Duminil-Copin has not exclusively worked only with the Ising model. Like I told you, the Ising model is defined on a lattice, but there is no reason for it to be defined on a lattice. It could be defined on an arbitrary graph, or what you can do is you have models related to the Ising model. One is called as the Fortuan-Castellan model, one is called as a random currents model, and there are some cousins here and there. So all those models were analyzed by him. So and of course the population model. So he analyzed all of them to some extent. The contributions of Hugo Duminil-Copin. Then of course, like Shubha mentioned, this book by Ramon van Handel, who had visited here by the way, when you were all not here. I spent a whole day with him. Probability in high dimensions. So this book that I have written here, right? This book is actually ideal for the entire seminar, because the seminar itself is called high dimensional probability. So if you have a book on high dimension, you pick it up. And then of course you have the cousin, which is Washington's. Washington high dimensional probability, not low probability. Right. Is there any other book that I can think of? This book by Bobby. I don't remember the name. I'm sorry. Jean. I think it's called Statistical Models in Physics. Or it's called Models in Statistical Physics. Statistical. So this guy contains rigorous proofs of Pearl's argument. It contains rigorous proof of dimension d equal to 1, and so on. Then there is a note by I have more references, I know it. There is a lovely note by Anton Capellas, which is called just one-dimensional and two-dimensional Ising model. So Anton Capellas, 1D and 2D Ising model. So what this guy will show is, this guy simplifies Ising's argument and shows that in one dimension there is no criticality, and he uses Pearl's argument, he explains Pearl's argument properly and shows how there is a criticality in two dimension. Okay. And is there any last? Oh yeah, this one. Okay, no, this one is only for Gaussian, only for those who stick around for Gaussian free field. It's a note by Schlickman called Topics in Occupation Times and Gaussian free field, but let's not discuss it.
You will take for undergraduate.
If you want me to try, I'll try, but if people go to sleep, then I have to take all of them.
So we can try this.
Everybody ready?
Yes. Yeah, right.
Actually, I didn't plan to cover this. I wanted to cover this like, I thought that people will sort of converse outside and I talk with them on a small level. But okay. If anybody wishes to leave, please feel free. Because this is not part of the talk. Like, this is not honestly part of what I'm doing.
Sir,
Thank you very much for attending. Thanks.
What's the
I think we can give a 5 minutes break or something.
Sir, can we start after 5 minutes? 5 minutes.
Okay, 5 minutes. Yeah. The difference is, the question was the following: what is universality? The idea of universality, which I am not going to explain about, I'll probably take like a minute. When that thing hits 12, the next time it hits 12, after this, I'll stop on universality. Okay? Okay, start. So universality is what? The idea is that you have different kinds of lattices, right? You have like the square lattice, you have like you can create various kinds of lattices. You can even create like a pentagonal lattice. You can create a hexagonal lattice. You can create your Pascal line type of lattice, right? On each of these lattices, you will have a version of the Ising model. The point is, can we say something like for all these models there is something common that is observed? That is the idea of universality. So the idea of universality is, what does it mean for something to be universal? It means that it applies in a lot of cases. So for example, CNT is universal in the sense that if xi are IID, then to a great extent, only thing you need to know is the variance. As long as the variance is finite, nobody cares about what the distribution is. You know that that particular asymptotic is n01. So that's an example of universality. only 10. So that is the basic idea behind universality. Okay? And I'm not going to explain more on that. So that is something that I'm going to leave Mr. HDC to. What is this Gaussian free field here now? What is this Gaussian free field and what is the weird complicated object that is making the life of so many budding mathematicians entering probability so difficult? Right. I mean, what is even a field for that matter? Maybe, one thing a field is definitely not is having graphs and it's not that. And neither is it the field that is there in mathematics. That is there in algebra. That is to say, the multiplicative structure, NAND structure, and invertible structure. Gaussian field. What is it? So, to define this, I need to define what is called the stochastic process. So, those of you who attended my lecture on stochastic processes will know what, will know of course what a stochastic process is, but they will know a lot of examples as well. In particular, they will know the example of what is called as a Gaussian process. So, I have to define what a stochastic process is and what a Gaussian process is, right? I think you guys came to me yesterday, I defined what a Gaussian process is, I'm just going to do the same thing. So, what is a stochastic process? So, given an index, so I'm not going to be formal, just given an index set t. So t is typically time, but in my case it turns out Gaussian free field is too complicated for me to take t as time. Index set t, a set of random variables x t, t in t, all of which have the same sample space. So all of which are, let's say, from omega to r. Again, it's not necessary that they all go to r, but they must have the same domain and codomain, that's for sure. It's called a stochastic process. It's called a stochastic process. Now, the reason why Gaussian processes, this is what I'm going to talk about next, are so special is because Gaussian processes are determined by just the mean and the covariance. So I'll explain what that means. So, a Gaussian process xt t in t on t is a stochastic process such that for all t1, t2, tn in t, this random vector, so it's not a random variable anymore, it's a random vector, essentially it's a random variable that takes values in Rd. So xt1, xt2, xtn is what is called as jointly normal. So as I said, I am not going to explain this, write it down and I will explain it to those who need the explanation later. And the second thing, so you can anyway ignore that part, don't worry about that. The second and the third thing is what is the mean and covariance, that's all. So the second is that the mean can be anything actually, so I am not going to constrain the mean right now. Later on I put the mean of everything equal to 0, I mentioned that. The second thing is there exists a function called k, which is from t cross t to r, which is positive semi-definite. Again, ask me what this is outside. Positive semi-definite. Such that the covariance of xt and xs is k of t comma s. For all t and s, that's all. The expectation of xt can be anything. Expectation of xt can be anything. Okay? So this is a Gaussian process. A Gaussian process is a process where each guy jointly, you take any bunch of finite guys, they are all jointly normal. But most importantly, you know the covariance. You know how one pair of random variables interact with each other. Okay? Now what is a Gaussian random field? A Gaussian random field is a stochastic process or a Gaussian process where this index set t is a pretty damn complicated object. So what is it? So, what is a Gaussian, discrete Gaussian field? So, discrete Gaussian field. Okay. By the way, for those of you who are a little bit shaky on the jointly normal and this positive semi-definite, ask me outside. Okay, I'll explain. I explained to these later. They'll also explain to you. Right. So, what is a discrete Gaussian free field? A discrete Gaussian free field is given a finite set X. Set X, a discrete Gaussian free field is a Gaussian process with index set, the set of all functions from sounds complicated, no? But I can't do anything about it. That is complicated. So, for example, what does a random variable here look like? A random variable here will look like xf, xg, xh. So, you will have functions on the bottom. Sounds very weird, right? We're used to having like x1, x2, x3. Suddenly I'm telling you there are functions on the bottom, like I have a splitting headache now. But it turns out that the best way to analyze these things, the best way to analyze, limiting properties of the Ising model is to introduce these discrete Gaussian free fields and then somehow show that the limit of certain quantities are these free fields. Okay? Now, I'll give an example of a discrete Gaussian free field that arises from a Markov chain. Okay? And what I'll explain is I'll also explain along with that this Markov chain CLT and the idea of why like a Gaussian free field is supposed to be like a really boring limit object.
Sarvesh,
What exactly?
Take
that next to
like X subscript F does even like denote.
xf is a random variable. xf is a random variable. xg is a random variable.
That's
xf is a
understandable.
random
Like if we are defining it on index at time, so x1 denotes that at time 1 the value is like.
Oh, it doesn't denote anything. I'm sorry. I'm deliberately keeping it abstract. So I'm not telling you, for example, I'm not telling you something like if f is less than g, then xf is less than xg or something. Please don't assume any such thing. Okay? So just for now, take it as a stochastic process. And what that means is, also note, what this means is once you have a discrete Gaussian process, discrete Gaussian free field, this covariance kernel will be like, it won't be k of t comma x, it will be k of f comma g. And what should you expect? What should you expect as that k of f comma g? You should expect k of f comma g as something like, I don't know, integral of f of x g of y something dy or something dy, something like that, right? So what is going to happen now is we are going to define something called the Green's function of a random walk, and then once we define the Green's function of a random walk, we will show that how that random walk has a natural DGFF associated. And what we will show is that DGFF ends up matching with the Ising model in dimensions 5 and higher. Okay? So there is some kind of limit here. So let's go back to this lattice. Okay. Now in this lattice, okay, no, pardon, you are not doing random normal lattice. You are not doing random normal lattice. So let's go back to the Ising model. Let's go back to the elements of the Ising model. So let's say, this is what is the sample space? So this is the state space. So omega from zd2 plus minus 1. Okay. And what you will do is you will restrict yourself to some finite d subset of zd, fix everything outside, some Gibbs measure or just fix everything outside, and assume that the Ising model is going on inside. Now when the Ising model is going on inside, those of you who have done a course in Markov chains will have heard of something called as Glauber dynamics. How many of you here have heard of Glauber dynamics? Take one Mysore cup. Okay. So what are Glauber dynamics? Basically speaking, imagine you want to create. So now you're a computer scientist. Okay, you're a computer scientist and you want to create a sample you want to create an element of sigma uniformly, or not uniformly, like you want to create it according to the Ising model. So you want to create a configuration of plus minus ones on V such that the probability that you create a particular configuration is given by the Ising model. So you are basically trying to simulate the Ising model as a computer scientist. The question is, how do you do that? And the answer is, you do it using a Markov chain and the idea of global dynamics. How does that work? So let's, for convenience, let's just assume that D is this 4-point set. Okay? Let's just assume that D is this 4-point set. What does global dynamics look like? So there are 16 possible configurations, right? So plus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. So how does, for example, the transition matrix look? So the Ising model, because it's an irreducible aperiodic Markov chain. So now, okay, sorry, I haven't defined global dynamics. Once I define global dynamics, I explain to you how it's an irreducible aperiodic chain. Right. What you do is you so you have the P, right? So you have P of sigma is as per Ising model. As per Ising model. So P, let's say P, okay? So now you have all these configurations, right? So what you do is, from a configuration, so you have a transition matrix, from a configuration sigma to a configuration sigma prime, it's 0 if sigma and sigma prime differ at more than 1 point. So if, for example, if in this configuration, let's say I have -1, -1, +1, +1, and I have -1, -1, -1, -1, then the transition probability from this configuration to this configuration is 0. Okay? But what is the probability that it goes to, say, some other configuration? What is the probability that it goes to, say, some other configuration? The probability of that is P of sigma prime divided by summation over all sigma prime adjacent to sigma of P of sigma. So sorry, sigma, let's say A, sigma. So what you do is, you look at all the guys that are adjacent to this configuration. So this is -1, -1, +1, +1. What are all the guys adjacent to this? So one of them is +1, -1, +1, +1. Another thing that is adjacent to this is -1, +1, +1, +1, and you can similarly write down the rest. For each guy, the Hamiltonian, you have a probability of that guy. For each guy, you have a probability of that guy, and you take this ratio. So you are more likely to go towards a lower energy state as compared to a higher energy state. If sigma, sigma prime differ at exactly 1 point. And to make this aperiodic, what you do is you will also include sigma A equal to sigma. So for example, if at most, so now what can happen is, a guy can come back to himself also. A guy can come back to himself also with a certain probability. Okay? So that is basically to ensure aperiodicity, don't worry about that. Even if the other case was okay, it doesn't matter. Now it turns out that global dynamics.
What is adjacent means? Okay, same thing.
Huh?
What exactly you want?
Sorry?
Adjacent, like sigma A.
Adjacent, I explained, right? So for example, let's say you have this configuration -1, -1, +1, +1, and you have another configuration where these three vertices are the same, but this is flipped.
Okay.
So that's what I mean by adjacent. Okay. So now you can run global dynamics, and what does global dynamics do? Global dynamics is basically this Markov chain that I have created. So this Markov chain is a Markov chain that is now created on the set of all configurations on B. Okay, and the point is, this Markov chain has an associated green function. So I'm not going to explain what exactly this is, but every Markov chain has an associated green function to it. What is this green function? This is as follows, right? What you can do is, suppose you have a subset W, which is a subset of the set of all configurations. So it's a subset of sigma from B to plus minus 1. Okay? What you can do is, you can look at, so let x comma y in W. Okay, let sigma 1 comma sigma 2. What I'm going to do is, so let me just draw some sigmas around. Okay, so these are not particles now; these are sigmas. Okay, so let's say these are some sigmas. This is W. Okay, this is sigma 1 and this is sigma 2. Okay, what I'll do is I start from sigma 1. Okay, I'll do the random walk. I'll do the random walk as per Glauber dynamics. Okay, so I'll walk. Okay, then I look at the number of times I visit sigma 2 before I get out of W. So at some point of time I exit W. Turns out with Markov chain that happens. Then I'll have to track the number of times I visit sigma 2 before I exit W. And the number of times I visit sigma 2 is basically the green function. So I start from sigma 1. Okay, I look at how many times I visit each vertex in W before getting out of W. Roughly speaking, the average of that is the green function. So let sigma the average number of visits to sigma 2 starting from sigma 1 before exiting W is the green function. So I am not going to make this rigorous. If making it rigorous will just require a little bit of machinery. This green function, let's call it as g of sigma 1 comma sigma 2, can be used to define a configuration. How does that work? I am not going to explain exactly how that works, but it turns out that this kind of configuration leads to a free field. So, wait, I'm not going to write it down rigorously.
By the way, what's a free field? Is the definition? Field?
Gaussian free field.
Oh, any Gaussian.
Any Gaussian. So, Glauber dynamics. By the way, it's not necessary that you need to do Glauber dynamics for Ising model. You can do this for Glauber dynamics on any random graph, and you can get a Gaussian free field corresponding to that particular set. Or some Glauber dynamics leads to a discrete Gaussian free field. Okay? Now, this is amazing. What happens is that now what happens is the following. Now what do mathematicians do? Mathematicians will do the following. Okay? Let's say this is the let's draw. Let's say this is in 2 dimensions. Okay, because I don't have the facility to do things in 3 dimensions. Okay? Let's draw the unit square. This is the unit square. And typically, when we're putting a Gibbs measure on the unit square, we might assume some kind of boundary conditions. I'm going to neglect that. But what I do is now I have various lattices on this guy. So one lattice will be like just 1 point. Another lattice will have 4 points. 1, 2, 3, 4. Another lattice will have 9 points. 1, 2, 3, 1, 2, 3, 1, 2, 3. Another lattice will have 4 points. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and so on. What I'm doing is I'm getting better and better lattice approximations of this square. So what will happen is each of these guys, executing like an Ising model on each of these guys, you will get these discrete Gaussian free fields. But the discrete Gaussian free field will depend upon the value of n. So for example, for 1 point you will get 1 Gaussian free field. For 4 points, so 1, 2, 3, 4, you will get another Gaussian free field. The question is, the discrete Gaussian free fields will depend upon n. So you will get some discrete Gaussian free fields which depend upon n. Okay, upon n. The question is, do they converge? Do they converge to a continuous Gaussian free field? So I'm going to write this in quotes because there is no way on earth that I can actually define what is a continuous Gaussian free field without confusing at least 90% of it and leaving the 10%.
What does convergence of a free field mean?
That also I'm not going to tell you. And take one myself. Okay, so I'm not going to tell you what that means. But what this tells you is that one way of analyzing the Ising model might be to actually go to these discrete Gaussian free fields and see if they converge. So this is one technique in some sense. And the thing is, why is this Gaussian free field so important? It's basically because it was observed that in dimensions 5 and greater, the kind of limiting behavior in some sense, I'll explain what exactly I mean, okay? I'll explain what exactly I mean. I'll define like the proper discrete Gaussian free field relating to the Ising model. So now, move it. Okay, right. So let's go back to the Ising model. So we have Sn, and we will have these sigma and the p sigma and whatnot. Let's keep that in mind. How will we define, for example, a discrete Gaussian free field in some sense? What we'll do is we'll define. First of all, we have to decide what is the index set of that Gaussian free field, right? We won't associate. It turns out that this is one approach, but this is not the approach that sort of is the most revealing in high dimensions. So in high dimensions, the proper revealing thing is to do the following. Have I written it down? I should have written it down. Perfect. So what you do is you take your index set. Please feel free to not write this down, okay? Because I am not making it rigorous. So we take your index set as the set of all functions from Sn to R, or let's not say Sn to R. Let's say R. We're in dimension 2. Say dimension 2. If we're in dimension higher, we can take RT to R, not a problem. Which is, let's say, smooth and compactly supported. Smooth, so it's C infinity, and it's compactly supported. What does compactly supported mean? It basically means that it is zero outside of compact set, so to speak. Compactly supported. What you can do is you will study these functions and how they behave for the Ising model. So because it's in R2, you can just restrict f to Sn. You can just restrict f to Sn and you will get a function from Sn to R. But you need to assume this kind of smooth, compactly supported stuff because you are going to the continuous setting. And in the continuous setting, you cannot afford to do all kinds of restriction business anymore. So once you take this index set as this, you define I and P. Oh sorry, I and F from Sn to R by I n f of sigma is equal to some n to the, so okay, this is actually size of Sn, okay, this capital N. So size of Sn to the something, some scaling exponent, something called an alpha, times summation over all the size, so summation over all I in Sn of the spin at I times the function evaluated at that point. So f of this sort of sigma, right? F is from R2 to R. Excuse me, just give me a second. How do I explain this? Okay, I'll write it down. So basically speaking, what you do is you kind of embed these configurations into okay, I won't explain it very clearly. But still, it doesn't matter. So the thing is, you can get these kind of functions, and now this is a stochastic process that you can show is Gaussian. So if I change f to something else, it turns out that this is a Gaussian field. So this I mod Sn f, where f is in some suitable family, let me call it a script f. Script f is a discrete Gaussian free field. And the thing is, this discrete Gaussian free field, as n goes to infinity, it will actually converge to a Gaussian free field on 0, 1. So that is a result in dimension 5 or greater that was predicted by mean field interactions and verified later. So why are Gaussian free fields not interesting? So it turns out that physicists claim that Gaussian free fields are not interesting. So the reason why Gaussian free fields are not interesting is basically because Gaussian free fields are predicted by mean interaction or by mean field interaction. So if you think about statistical physics, if you think about what physicists want, if you go back to the Ising model, you have 2-point interactions, and in the mean field, if you do the mean field approximation, they become like 1-point interaction. Like each guy is interacting independently with the average of the rest of the guys, like that, right? Now this reduction, it worked in high dimensions, and when it worked in high dimensions, the limit was a Gaussian free field. The thing is, a Gaussian free field, I'm not going to explain this very rigorously, but a Gaussian free field is typically associated with a heavy amount of independence. So to illustrate that, you have this Markov chain central limit here that tells you that if you are running a Markov chain starting from the station distribution, then there's like a CLT associated to that. So number of times, like, so either like if you take any statistic like G from state space to R and track G of xi, that G of xi will have a particular CLT associated to it, whose limit is normal. So normal is typically associated with a heavy amount of independence. Whereas those of you who have seen limit laws where the limit isn't normal, like Gumbel, like some kind of extreme value statistic or something like that, what happens is that in such models there is a heavy amount of dependence. So if I had to put this in a nutshell, Gaussian free field limits are if and only if some kind of interactions between particles is asymptotically independent. So what that means is that at some scale if there is some interaction and at a high scale there is another interaction, all those interactions are becoming weaker and weaker and weaker as n goes to infinity, and at the end of it, if that happens, then you should expect a Gaussian free field limit. On the converse, if Hugo Duminil-Copin tells you that something has a Gaussian free field limit, what you should think is, oh, in this model, these interactions vanish so much to the extent that there is almost a mean field type of behavior. Okay, so I'll write this down. Gaussian free field and its association with this mean field interaction. So Gaussian free field is basically heavily independent. Okay, so Gaussian free field and heavy independence. Heavy independence. So it turns out that okay, I should mention green function. I'll put green function. Green function. Okay. Global dynamics. Okay, maybe global dynamics. I don't think global dynamics will come first. Okay, so the thing is, in Hugo Duminil-Copin's talk, whenever you hear the word Gaussian free field, imagine that what is actually happening is that these interactions with large n between particles are weakening to the extent that the mean field regime is coming into. Okay, so this is what pretty much I had to say. I think this is pretty much what the advantage I have. I have some other things. So for example, I have a list of like explicit calculations in 1 dimension and 2 dimension, which I took from Cardano's book. Then I have a statement of a Markov chain CLT, but that I'll explain later. And yeah, that should really be it. That should properly be it. Yeah, I'm done. You guys are ready for this talk now.
Okay, thank you, Sarvesh. So, any questions from anyone?
Mysore Park.
For Mysore Park?
Take.
No, no. Questions for Mysore so that they
Oh, I
can
said
answer.
so.
Any questions? If there are no questions, then that's it.
What was the scaling relation for identity? What you stated for block phenomenon? That was it.
Sorry, what is the?
What was like the scaling relation for identity?
It's the following. The prediction. Okay, this is not the answer. Oh wait, are you talking about under mean field?
Yeah.
Under mean field, you have that exact behavior. So you can find so in dimensions greater than or equal to 5, I think there exists b which depends on d greater than 0, such that limit m tends to beta tends to beta c from the top of beta minus beta c to the capital D upon m beta exists and is positive and is finite. So this is predicted by mean field. Very good. In fact, Mean field will even tell you what V that is. VD is just B plus 1 by 2. VD is just B plus 1 by 2. And it turns out that, remember I wrote some alpha here, this alpha will also be D plus 1 by 2. So with this D plus 1 by 2, you will actually get this kind of scaling to a Gaussian field. I need to make that way more precise if I need to go into proper detail. But roughly speaking, this is predicted and I think this has been proved. This is basically proved by the fact that you can equate it to the mean field interaction. This is like a second order statement, right?
Could you explain that f of sigma by n again?
No, that's very difficult. I'm sorry.
Okay.
I'm actually really sorry. But the thing is, the problem is what you have to do is you have to somehow embed all these configurations itself within the square. So I'm not going to, I think I've I wrote it down, but then I think what I've written down is incorrect. So that's the problem. But if I once if you give me like 4-5 hours, I can get back to you. But basically what's happening is you can create a Gaussian free field. You can create a Gaussian free field corresponding to the essence. Let the n goes to infinity and observe that the discrete Gaussian free fields will converge to a continuous Gaussian free field. But what will happen in dimensions 2, 3 and 4? So in dimension 2, using those exact calculations, Hugo Duminil-Copin proved that when alpha is equal to 15 by 8, don't ask me where that came from, this converges. This is a Gaussian free field, yes, but there are such strong correlations in this Gaussian free field that the limit is not a Gaussian free field, it is something else, or something that I am not going to discuss. It is a free field which is not a Gaussian, it has worse correlation degree. So I told you, right, the correlation is like some k of t comma s. That k of t comma s does not have like a Gaussian flavor to it. That is basically what I want to say.
Now I have one question. We define what is Gaussian free field, but what is just a free field?
What is just a free field?
Yeah.
Is where you will have what is just a free field? No, what just a free field is like you just have a stochastic process with that guy's index that if I'm not wrong. Where I think if you assume some kind of independence or something, you will get free for the word free. Actually, I don't remember, I don't recall. Because I have only heard the word free with the Gaussian code behind it. So I don't know. And one more problem is, I have given you one definition of Gaussian free field. There are like 5 definitions. There is something Gaussian definition, there is a definition for Hilbert space, then there is a definition where like the index set is not functions but the index set can be taken to be vertices. So, but that definition is not convenient, it's not convenient. So, the basic thing you have to realize is every discrete Gaussian function, or at least there is a connection between this kind of global dynamics or Markov chain on a particular graph and a discrete Gaussian free field associated to that graph or that model. And these discrete Gaussian free fields are nice because you can like talk about you can think about what limits they might have. You can think about their statistics. You can analyze like a discrete Gaussian free field is a stochastic process, right? So you can have xf. You can ask, okay, what is the expectation of xf? What is the variance of xf? Questions like that. So questions like that are very natural. And there are books by I said I have references. There is a book by Sneakman. Sneakman, I forgot what the first is, but it's called this and Gaussian free field. But I think you guys are more than ready to see his first talk, because his first talk is going to be very basic, I guess. It's going to mostly cover, it won't cover these things, it may cover things in more detail, and he'll throw more terminology around. But like you guys are, I think 70 to 80% ready for his first talk, even the first year. Those who didn't come for the second part of the session also, they are ready. Those who came for this part should be 90 to 95% ready. Unless and until he changes model, like he changes his lattice or he starts talking about universality, then you have a bit of trouble. But otherwise, we should be okay. This is Hugo Duminil-Copin's first talk. Second talk onwards, I cannot give any guarantees of what.
Is it topics in occupation times and not in
Occupation times?
So any more questions, anyone? If there are no questions, so